All right, so now that we've learned about derivatives and how they function, we're going to put them into their actual application or real-world applications. Now, remember, derivatives of a function always represent a rate of change. So problems involving the movement of a particle are usually described as a function of time, t, if we're given a function that describes the position of a particle at any time t, then we can use derivatives to determine functions that describe the particle's velocity and the particle's acceleration at any time for t. So we can say that if y is equal to st, the displacement and the time, then dy over dt, or the derivative, is going to equal s prime of t, which is just the velocity given a time. There's our velocity. We can also state that the second derivative is going to give me my acceleration as a function of time. So the derivative of our velocity literally is acceleration. We do this in terms of our position, which is going to be represented by s, and it's the displacement of an object from a reference point with respect to time. Make sure that you recognize that that is not the total distance that is traveled. It's looking at where something started and where something ended up. And the velocity is the rate of change in position with respect to time, which often we use the term velocity interchangeably with speed. And there's a difference between average velocity and instantaneous velocity. Remembering that when we take the average, that's going to be the slope of the secant. And the instantaneous is our slope of the tangent. So when we look at average velocity, we're looking at two different positions over two different times, and then we're just dividing it using our slope formula. So like it says, picture a secant line on a graph drawn between 2 points on a curve. So if I have a graph, I have a curve, and then I'm taking 2 points on that curve and finding what the slope of that is using my rise over run. So I have my change in t, and I have my change in my s. If I'm doing instantaneous velocity, then that is going to be from the tangent line, or the derivative, as t approaches 0, or the change in t approaches 0. Which means that that would be similar to the first one, except for, in this case, if I'm doing it along the curve, then it's literally what is the slope at one exact point where it touches the curve. Acceleration, which we always use lowercase a for, is the rate of change in the velocity with respect to time, and we're going to address specifically acceleration in lesson 2. Remember, in application problems, if y is equal to f of x means something, then y prime is equal to f prime of x means something else. If f of x is a position of a function, then f prime of x is the related velocity of the function. So f of x is the position at a specific time. Like if we are looking up here, there is the exact position at that exact time. F prime of x for the same one is going to be what is the slope at that exact point. There are a few things to know about velocity. If velocity is equal to 0, the particle is at rest. If the velocity is greater than 0, the particle is moving in a positive direction, which graphically we always think of as either up or to the right. And if the velocity is less than 0, the particle is moving in a negative direction, and negative in this context is either down or to the left. If you're asked to find what is the velocity, then that means what is the instantaneous velocity. All right, so let's take a look at example 1. So it says, if a stone is dropped from the top of a cliff that is 122.5 meters high, then its height in meters after t seconds is given by the function h is equal to 122.5 minus 4.9 t squared. And this is where t has to be greater than or equal to 0. We can't go backwards in time. So when it says find the velocity of the stone after 1 second, well, we know that if our function is h as a function of t is equal to 122.5 minus 4.9 t squared, then that means that our velocity is going to be the first derivative of that function. If I take the first derivative of that function, it's going to be negative 4.9 times 2t, or negative 9.8 t is always going to tell me my velocity. So when it says what is the velocity of the stone after 1 second, now really what it means is at 1 second. Remember, this is always an instantaneous velocity that's occurring. So I'm going to say that the velocity at 1 second is equal to negative 9.8 times 1, or negative 9.8 meters per second. Don't forget to use those units. When it says, what is the velocity after 2 seconds or at 2 seconds? Same idea. The velocity at 2 seconds is going to be negative 9.8 times 2, which is going to give me negative 19.6 meters per second. Now, sometimes I get asked, why is this always negative? Well, it tells us right up here that the stone is being dropped, which means that the stone obviously is going to keep heading downwards. And if I'm thinking of it in terms of physics, if something's going down, it is always going to be negative. When it says, when will the stone hit the ground? Well, the stone is going to hit the ground when the height is 0. When it says when, that's just saying what is the time. So I'm going to replace the height with 0 and say that for my equation, my original equation, remember where it was actually solving height up here, that I'm going to have if h is equal to 122.5 times negative 4.9 t squared, then that's going to equal 0 because my h is equal to 0. This means that positive 4.9 t squared is going to equal 122.5. And when I divide both sides by 4.9, I get t squared is equal to 25. Now remember, when I'm square rooting this, I would think of it in terms of the positive and negative square root, which means that I would actually get the answer of t is equal to negative 5 or positive 5, but that's why we remember that it said that t has to be greater than or equal to 0, which means that the negative 5 answer doesn't make sense. So what would I say? I would say that the stone hits the ground five seconds after it is dropped. When I translate that to part D, where it says, with what velocity will the stone hit the ground? Well, we solved the time for when the stone hits the ground. So I'm just going to be solving the velocity using the same formula I did for part A and B, but I'm going to use it with my new time, which is 5 seconds. So I'm going to say that the velocity at 5 is going to equal negative 9.8 times 5, which is going to give me, in this case, negative 49 meters per second. The velocity when the stone hits the ground is 49 meters per second.